Your computer just loaded this video in a fraction of a second. In that same blink, it ran billions of tiny calculations. But here's the thing nobody tells you. Your computer doesn't actually know what a video is. It doesn't know what YouTube is. It doesn't even know what the number 5 is. All it does, all it's ever done, is follow a very simple loop. Fetch an instruction, decode it, execute it, repeat, a billion times per second. Today, we're going inside that loop. We'll meet the CPU, shake hands with RAM, expose some myths that tech salespeople love, and show you what's actually happening when you game, compile code, or just open 17 browser tabs. In 1945, a mathematician named John von Neumann wrote a paper that's arguably the most consequential engineering document of the 20th century. He described a simple machine with 4 parts: a processor that does math, a memory that stores data and instructions together, an input-output system, and a single bus connecting them all. That design is called the von Neumann architecture, and almost every computer you've ever touched, from the Apollo guidance computer to the phone in your pocket, is built on that exact same blueprint. Now, the von Neumann bottleneck is a real phenomenon. Because instructions and data share the same memory bus, they can only travel one at a time. Most CPU innovations since the 1970s have been attempts to work around this. The first computers using this design filled entire rooms and consumed as much power as a small neighborhood. ENIAC, built in 1945, weighed 30 tons and could do about 5,000 additions per second. Then, in 1971, Intel released the 4004, the first commercial microprocessor. It crammed the entire CPU onto a single chip the size of your thumbnail. It had 2,300 transistors. Today, Apple's M-series chips carry over 100 billion transistors on a chip that you can cover with your thumb. The key driver? Moore's Law. Gordon Moore's 1965 observation that the number of transistors on a chip doubles roughly every 2 years. It held up for decades, though now we're hitting physical limits at around 2 to 3 nanometers, where transistors are just a dozen atoms wide. By the mid-2000s, chip designers hit a wall. They couldn't just keep cranking up clock speed. The chip would get too hot and consume too much power. So instead of making one worker run faster, they hired more workers. That's multi-core. A dual-core CPU has 2 complete processors on the same chip. Quad-core has 4. Modern desktop chips often have 8, 16, or even 32 cores. But more cores aren't always better. If software isn't written to use multiple cores, called parallelism, extra cores just sit idle. A single-threaded video game can't use your 32-core CPU any more efficiently than a 4-core one. Every CPU, from the cheapest microcontroller to the most powerful server chip, runs the same fundamental loop. We call it the fetch, decode, execute cycle. Think of it like a chef in a kitchen. The recipe book is memory. The chef's eyes are the fetch stage. They read one instruction at a time. Dice the onions is the decode stage. Understanding what to do. Actually dicing is the execute stage. And putting the result in the bowl is the write back. Then the chef reads the next instruction. Now your CPU does this cycle between 3 and 5 billion times per second. Inside the execute stage lives the ALU, the arithmetic logic unit. It's the only part of the CPU that actually computes anything. It can add, subtract, multiply, divide, and perform logical operations like AND, OR, and NOT. That's it. No magic. Your CPU isn't understanding the video game you're playing. It's just doing millions of these tiny arithmetic operations per second, and the combination produces something that looks like a dragon breathing fire on your screen. Before the ALU can do anything, it needs data to work with. But fetching data from RAM takes time, hundreds of clock cycles. So modern CPUs have registers, tiny, blazing fast storage locations built directly inside the chip. A modern CPU has maybe 16 to 18 general-purpose registers, each holding one piece of data. If the ALU is the chef's brain, registers are the chef's hands. Only a few things fit, but access is instantaneous. Between the lightning-fast registers and the relatively slow RAM, there's a buffer zone, the cache. Modern CPUs have 3 levels. L1 cache is the smallest and fastest, typically 32 to 64 kilobytes per core, accessible in 1 to 2 nanoseconds. L2 is larger and slightly slower. L3 is shared between all cores, often 12 to 64 megabytes, and is slower still. But 10 times faster than RAM. Well, back to the kitchen analogy. RAM is the pantry down the hall. The cache is the prep counter right next to the stove. You batch fetch ingredients from the pantry and keep them on the prep counter so you don't have to keep walking back. Now, here's where things get clever. A naive CPU does one step at a time. Fetch instruction 1, decode instruction 1, execute instruction 1, then start instruction 2. But modern CPUs pipeline those steps, like an assembly line. Multiple instructions are in different stages simultaneously. Even more impressive, out-of-order execution. If instruction 5 doesn't depend on the result of instruction 4, the CPU can jump ahead and run instruction 5 early, keeping the ALU busy instead of stalling. This is also why the infamous Spectre and Meltdown security vulnerabilities existed. CPUs were speculatively executing instructions before checking permissions, and clever attackers found ways to read the residue of that speculation. RAM stands for Random Access Memory. Random access means that you can retrieve any byte of data in the same amount of time, regardless of where it is, unlike a cassette tape, where you'd have to rewind to find something. Think of RAM as your desk. When you open an application, the operating system copies it from your storage drive to the desk. Now the CPU can grab pieces of it quickly. The bigger your desk, the more you can have open at once. This is one of the most common confusions in computing, and tech ads love to muddy the waters. You've probably seen a phone ad that says 128 gigabytes in giant letters. Well, that's not RAM, that's storage. The phone might have 8 gigabytes of RAM, buried in the fine print. Here's why it matters. If your RAM fills up, your operating system starts using storage as virtual memory or a swap file. Suddenly, instead of 60 nanosecond access times, you're waiting through millisecond scale access times, thousands of times slower. This is why opening 50 browser tabs makes your computer feel like it's running in sand. Let's bring it all together with a library. Imagine you're a scholar in a medieval library. The books you're actively reading are on your desk. Those are registers. The shelf right behind you holds a dozen books you grabbed this morning. That's L1 cache. The bookshelf across the room holds a few hundred books. L2 and L3 cache. The main library stacks hold thousands of books. Well, that's RAM. And the offsite archive in another building, where rare books are stored, requires you to send a letter and wait for delivery. That's your SSD or hard drive. The CPU always tries to work from the desk. It only walks to the shelf when the desk is full. It only goes to the stacks when the shelf is empty. Every trip to the archive is painful. When you're playing a first-person shooter, your CPU is doing something specific every frame, running game logic, physics calculations, AI behavior, collision detection, input handling. That's the CPU. The GPU handles the actual rendering of pixels. The bottleneck for gaming is usually GPU-bound. The CPU finishes its work and waits for the GPU to catch up. But CPU performance still matters enormously for simulation games, strategy, city builders, RPGs with lots of entities, where the CPU is juggling thousands of calculations per frame. Cache performance is crucial here. The game needs to constantly access a small working set of data, nearby entities, current map state. Processors with large, fast L3 caches show measurable improvements in these workloads. Compiling source code into an executable is one of the most demanding single-threaded CPU workloads that exists. The compiler must parse text, build an abstract syntax tree, optimize code, resolve symbols, and emit machine instructions, all in sequence. This is where clock speed in IPC, instructions per clock, genuinely matter. Developers who compile code all day see the most dramatic real-world improvements from faster CPUs. Apple's M-series chips became famous in developer circles partly because compile times on large codebases dropped by 40 to 60% versus Intel equivalents. Modern compilers also parallelize across cores, compiling different files simultaneously. This is where having many cores actually helps. A 16-core chip can compile 16 translation units at once. Here's the surprising truth. Your CPU isn't actually doing multiple things simultaneously, at least not on a single core. It's switching between tasks thousands of times per second, so fast that it creates the illusion of parallelism. This is called time slicing, and it's the operating system scheduler doing the choreography. When you have more tasks than cores, the scheduler assigns each task a tiny slice of time, maybe a millisecond, then pauses it, saves its state, and loads the next task. This context switch has a cost. The CPU's cache gets polluted with the new task's data, flushing out the old task's carefully loaded context. This is why your laptop doesn't literally freeze when it runs out of RAM. The scheduler keeps everything moving, just very slowly, as the system thrashes between RAM and virtual memory. This one sells CPUs and confuses consumers. Gigahertz. Well, that's your clock speed. How many times per second the CPU ticks. But one tick of a 3 GHz Apple M4 chip accomplishes far more than one tick of a 3 GHz Intel chip from 2005. Because IPC, instructions per clock, has improved dramatically. A CPU running at 3.5 GHz with modern microarchitecture will crush a 5 GHz chip from a previous generation. Clock speed is one variable in a complex equation. Adding RAM helps, until you stop hitting your limit. If your system uses 6 GB of RAM and you have 8 GB, upgrading to 16 GB will do nothing. Upgrading from 8 to 16 GB when you're regularly hitting the ceiling can be transformative. The sweet spot for 2025 is 16 GB for general use and productivity, 32 GB for content creation or heavy development work, and 64 plus GB for video editing, 3D rendering, or data science workloads that load large datasets into memory. Say it with me. RAM is not storage. RAM is not storage. Closing that app does not free up storage. Your storage is not full when you have 20 tabs open. These are different physical components doing fundamentally different jobs. The confusion comes from marketing and from unified memory architectures, like Apple's M chips, where the GPU, CPU, and RAM share one physical pool. That's not the same as storage. It's still volatile RAM. It just also serves as GPU memory. So here's what you now know that most people don't. Your computer is running the same von Neumann blueprint sketched in 1945. Your CPU executes a billion fetch, decode, execute cycles per second, deferring to a hierarchy of increasingly slow memory to find what it needs. RAM is your desk, temporary and fast. Storage is your filing cabinet, permanent but slow. Gigahertz is not a simple proxy for speed. And more cores only help if the software knows how to use them. Every time you click a button, open a file, or launch a game, you're setting off an invisible avalanche of these tiny operations, all coordinated by an operating system that's been refining these tricks since the 1960s. Next time, we're going one layer deeper and one layer darker. We're going to ask, what happens when someone tries to break that system? We'll trace the origins of cybersecurity, from early phone phreakers and Cold War mainframes, all the way to the vulnerabilities hiding in the cache hierarchy we just talked about.